Welcome to Train Signal. You are watching Tuning vSphere Performance. So a couple of, kind of higher level ideas here before we get into some more of the technical details. But first of all, there's really two main types of hypervisors. There's the hosted type, like VMware Workstation for Windows Linux, or VMware Fusion for OS X for Mac, like what I'm running PowerPoint on Windows on right now. And then we have the bare metal hypervisors, ESXi, Zen Server, maybe KVM, maybe Hyper-V, depending on how you look at and handle your definitions. But really, things like that are purpose-built hypervisors. They are not basically applications that run on top of another OS. And those bare metal are closer to the hardware, so you get better performance and more stability. So let's talk a little bit about ESXi's components. So first you have the actual hardware, the server, the physical components, if you will. And then we have the device drivers for NIC or I/O or disk or anything like that. And these are specific ESXi drivers for that specific piece of hardware. So it doesn't just use any Linux driver or anything like that. There are specific ESXi drivers. And then we have the VM kernel, which is kind of the ESXi operating system kernel. It's what does all the really intelligent work within ESXi. Each time a VM starts, we have what's called a virtual machine monitor, the VMM. It's a thin software layer that abstracts the physical hardware from the VM. So it's kind of that shim, if you will, between what a guest OS sees and the actual hardware. And then you have the scheduler, which is responsible for managing VM processes and threads and getting them run on the CPUs and the cores. Here is a quick diagram kind of showing and outlining the components. So at the bottom, we have your physical hardware, we have your device drivers, then we have things like, file system drivers for VMFS, we have virtual switch, virtual NICs, memory allocator for allocating virtual memory to physical memory, scheduler, which schedules virtual CPUs to physical hardware, and then we have the actual stuff within the guest OS. So it's just a layered approach. Just know what each piece does as we talk about them through other lessons, especially when we talk about CPU scheduling and memory allocation. So managing performance on virtual workloads adds other dimensions than physical workloads. You got the overhead of the hypervisor. You have multiple VMs running on the same physical host, possibly causing scheduler contention for getting threads scheduled on CPUs. Then you have, what I'd consider to be another dimension, which is load across the cluster, so that you have some hosts that are busier than others, and we have things like DRS to help balance that. But it gets a bit more complex to kind of, manage the performance. And these things can make performance troubleshooting a bit more complex. The idea is try to narrow down and figure out where the problem is and see if it's a problem in that VM or due to other VMs or overload of the host. So when we look at things like ESXtop and other lessons, we'll see these things. We'll see where we check the performance of a host or performance of a VM and try to narrow down those problems. So talk a bit about tuning the virtual machine monitor, and this is one area that I think is very testable by the exam. So remember, the VMM is that thin software layer that abstracts physical hardware to the VMs. One VMM is started per virtual machine by the VM kernel. There are three different VMM modes: software virtualization, hardware virtualization, and what we call para-virtualization. Choosing the correct. So when you virtualize a CPU, it really consists of a couple of things. We have virtual instruction sets, virtual memory management units, MMUs as we say, and we have multiple ways to virtualize these, called the monitor execution mode. And you get to set that execution mode. So again, this is very testable for the exam, is making sure you select the right one. Odds are you've never selected any of them, you just let vSphere do it. So that's why it's a great thing to be tested by the exam, because it's one of those things you don't commonly do. Normally, ESXi does determine the best one. They are settable, and they can change depending on the hardware that you're using and the capabilities, and you can override it if you want to. So software and hardware monitor mode. Software mode is used if the system hardware doesn't support virtualization. It inserts software, what we call under the virtualized OS, and the software, the VMM, runs in CPU ring 0 and performs binary translation to fool the guest OSs. So this is kind of old school way to do it. If you know anything about CPUs, they have what are called rings. Ring 0 is the most powerful, and then you go out to ring 1s, 2s, 3s, and 4s. And so basically the VMM inserts itself into 0, which commonly, like the Windows kernel, would sit at 0, but instead the VMM does, and it does binary translations. And anytime you do have a piece of software doing binary translations, your performance suffers. So the software mode is often the slowest method. And there you go, slower than the hardware method. Modern server hardware supports virtualization directly. Intel has VTX, AMD has AMD V, and by modern, I mean really anything made in the last, I don't know, several years, probably anything that is reasonably under support and maintenance. Removes the need for the VMM to do binary translation, so it gives you better performance. The VMM runs in what we call root mode, which is actually below ring 0, and the guest OS still runs in ring 0, but you don't have to do the binary translations, which again makes it quicker. So in the end, remember, software slow, hardware fast. Normally the VMM is very efficient, maybe 1 to 2% overhead, and that's why when people say, oh, we can't possibly virtualize a server, the overhead is too great, and I just kind of look at them all quizzically, and sometimes I'll say, well, you know, are you running this thing at such a performance index that 1 or 2% is the difference between success and failure? And the answer to that question is always no. Nobody runs things at that kind of a, you know, on the edge of performance, which is why there's about nothing that we don't virtualize these days that runs on, you know, the x86 platform. Some functions do cause latency, fault handling, interrupts from devices, and I/O requests. There's really nothing you can do about it. The reason I'm telling you this is just for your information and to understand kind of how the platform works. But even if you're not using virtualization, fault handling, interrupts, and I/O requests still cause a performance hit straight to an OS. It's just something where the hardware has to stop what it's doing and handle that, and it just, you know, slows down everything else. The CPU scheduler is responsible for scheduling, vCPUs on physical CPUs. And it supports multi-CPU physical servers and VMs. It uses what we call a relaxed co-scheduler. Relaxed meaning it tries to schedule like multiple virtual CPUs as close as it can together, but it doesn't have to do them all at the same time every time. If it had to do them, you know, if you had a 4 vCPU VM and it had to schedule all 4 of those vCPUs at the same time every time, it would be tough to share CPUs and sockets and be able to actually manage that. So it's called a relaxed co-scheduler. It is aware of the physical system. It needs to be so it's intelligent, so it knows how many CPUs and how many cores. It understands CPU level 1, level 2, level 3 caching, and it understands what we call NUMA, or non-uniform memory access. And it needs to understand this stuff to adequately schedule things. It tries not to move CPU threads from one physical CPU to another, because if we do that, the cache that was on the old CPU is useless to us now. So it tries to keep things on the same CPU. With NUMA, non-uniform memory access, you have memory basically direct attached to CPU sockets. If you have a 2-socket server, half your memory is normally owed to one, half to the other. A thread can access memory on either, but it accesses the local attached memory faster, so the scheduler tries to keep things where the local memory access is. So there's things that it does to be more intelligent and increase performance. So I just kind of ran through the spiel on this, but modern servers have CPUs with directly attached RAM. So processors running on the CPU have fast access to the local RAM. Accessing RAM on a different CPU is not as fast. It's still fast, but it has to go through a hop to get there, so it has a bit higher latency. The scheduler tries to keep processes on the same physical CPU to take advantage of cache and memory, but you can override these things. My recommendations are try not to assign more vCPUs to a VM than a CPU has cores. You don't want to split vCPUs across multiple CPUs. And then you have basically logical cores or hyper-threading, where a single physical core can execute 2 threads in one cycle, but it's not always like that. It depends on the execution, depends on the pipeline, on a lot of things, so you can't count on it. So don't assume that a 6-core CPU with hyper-threading is at 12 cores, so you can put a 10-core virtual CPU VM on it. It's not like that, so don't over-allocate. Try not to assign more RAM to a VM than is available to a NUMA node, meaning you got a 2-socket system. You got 48 gigs connected to one, 48 gigs connected to the other for a total of 96 in the system. Don't create a 64 gigabyte VM, because no matter what, there's going to be some non-local memory access there. It's going to split across the NUMA nodes. So it's best practice to do only up to 48, really consider an overhead a little less than that, or add memory to the server so you have more than you need on each NUMA node or each CPU with direct attached RAM. In high CPU situations, the scheduler may need to move vCPUs to other nodes, which does have a performance impact. So you can go into ESXtop and see what we call NUMA locality, and see if it's having to jump across to other memory and things like that. And it's just one thing to look at. Another one is ready time. Ready time is the amount of time a vCPU tries to execute but can't due to load. It has to sit idle for a while and impacts workload performance. Big reason you should not overassign virtual CPUs is it causes scheduler overhead. And you can monitor ready time both in vCenter and ESXtop. Lower is better. So I believe vCenter in the performance chart shows the number of milliseconds that a thread or a vCPU is waiting to execute but couldn't, and ESXtop shows it in a percentage. I like the percentage. You can convert back and forth, but to me a percentage is easier. So basically this is what happens. We got a bunch of virtual vCPU VMs running on our host. The application vendor said, no, you don't understand. This thing's got to have 4 vCPUs or 4 CPUs or 8 CPUs or whatever. We can't let you go to 2. Don't care what you think. Got to do it, or we won't support you. You see that everywhere you go. So you get all these VMs with 4 or 8 vCPUs. The problem is a scheduler's trying to schedule this. So if you've got a VM with 4 vCPUs and it's running Windows guest, Windows expects those 4 vCPUs to be executing threads relatively close to each other. The time difference between them is called skew. We don't want the skew to be too much, so the scheduler tries to execute them in a proper order. But if I got 4 vCPUs, there's 10 more 4 quad vCPU VMs on the host, it's having to manage all this. And sometimes it gets to a point where it can't. So it says, okay, Mr. Windows guest, I'm going to hold you for a second while I execute this guy, and then I'm going to hold this guy while I execute that guy. And while you're standing there, hold with work that needs to be done, but the scheduler can't schedule all the threads, that is called ready time. The VM is ready, but it can't be scheduled. What you want to see is 10% or less. Multi-vCPUs, you can go a little bit higher because it's an aggregate number. Like, if you have 4 vCPUs, that percentage time is the total number. But I like to see less than 10. With multiple vCPUs, you can go up some, but I like to see less than 10%. And then you have virtual memory management. So VMs don't see the actual physical RAM, like they don't see the actual CPUs. They see an abstraction. Virtual memory seen by a VM is mapped to physical memory. I mean, the stuff has to be stored somewhere, right? It's got to be stored in a physical memory, just like the Windows VM I'm using right now on my iMac. This stuff we're looking at is stored in RAM. It's just the RAM that my Windows guest sees is just abstracted from the 16 gig of RAM in the iMac here. And that's what Fusion is doing, and that's what ESXi does. Guest OS uses page tables to map virtual memory addresses to physical. The guest OS isn't aware of the change. He thinks he's writing to physical memory. VMware ESXi is fooling him. Modern servers support a translation look-aside buffer, TLB, which increases performance. Again, as virtualization has gone more mainstream, we see hardware vendors taking advantage of making it run quicker. What you really need to know about memory is the overcommit method. So using memory overcommit saves on resources, but can become a constrained resource. So yeah, you can have 64 gig at a server and have 200 gigs worth of memory assigned to VMs all running at the same time. But what happens when they all need to use more than 64 gig? There's a couple of things. First thing it does is transparent page sharing. It's owned by default, but not always used. We'll talk about that in a second. But basically, if you have 20 VMs all running Windows on a host, do we need 20 copies of all those DLLs in memory? Short answer is no. We'll have one copy and just reference it. That's transparent page sharing. It's trying to find common memory pages and deduplicating them, basically. Then we have ballooning. So this is why you want to have VMware tools installed of all your guests, because ballooning says, okay, we're starting to run out of memory on the host. Windows grabs memory, use it for file caching and other things, but it'll hold on to it thinking, well, I've got full access to the hardware. There's no reason to let this memory go unused. I'm just going to put file cache data in it. What happens when we need that memory back? Well, vSphere goes to the VMware tools inside the guest and says, hey, we need some memory back. So the VMware tools balloon driver goes and starts requesting memory from Windows, and Windows is going to pull it out of the file cache area first, gives it to the VMware tools balloon driver, and the balloon driver then releases it to vSphere, and it's basically a way to reclaim low priority memory that wasn't really being used. So that's your first line of defense. Okay, we've transparent page shared all we can. We've ballooned back all we can from all guests with VMware tools. but we're still running out of memory. So a new feature in 5 is memory compression. So before we start swapping stuff to disk, we start compressing it, basically zipping memory as best we can. And so if you ever see this in your performance charts or under ESX tops, it means you're about to start swapping to disk. So we compress. We're still running out of memory. We start swapping to disk, which is awful. Because you think, well, why is it so awful? All operating systems page to disk, right? Windows does it, OS X does it, Linux does it, yeah. But when Windows swaps stuff to disk, Windows knows what he's using and what he's not, so he tries to swap the stuff that's just stored in memory but not being actively used to disk first. Same with Linux, same with OS X. When vSphere swaps to disk, it's just swapping memory to disk out of the VM. It doesn't have visibility into that VM to know what's good and what's bad. It just starts swapping. Your performance goes through the floor. So add more RAM, or add more hosts and more RAM. So again, transparent page sharing, ballooning, then memory compression, then swapping. You can use host cache for faster swapping, so a new feature is to assign SSDs for that function, and you can do that, and it allows you to swap cache to a faster SSD disk. And you manage that through the device properties for that SSD. Every time you boot a VM, it takes the memory that you've assigned to it. Like on the right there, I've got an example with a 1 gig assigned. And then there's memory overhead, 27.25 meg. So you need to keep some stuff in mind. So first of all, the VM kernel itself uses about 100 meg. And then the VM overhead is based on RAM and vCPUs assigned. So if you assign an 8 vCPUs and 16 gig of RAM, it's going to have more memory overhead, which is a great reason to beat back those application vendors and say, no, 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 you don't actually need that many vCPUs. So you'll see that it starts using more and more for overhead. And you can see this in the VM summary screen right there on the right. So if you look at every of your VMs, you'll see exactly how much overhead is being used. A couple of memory recommendations. Use large memory pages when possible. Makes things faster. And those are owned by default. Basically, those provide 2 meg memory pages instead of the smaller pages. There's a big downside to those things, though. You can't do transparent page sharing because OSs figure 2 meg is a lot of stuff. And there's probably about 0 chance I'm going to find a couple of 2 megs pages that are exactly the same. Therefore, I'm not even going to bother, and it doesn't. It'll switch to small memory pages under heavy contention. So as memory gets used, you start going to 89% on a vSphere host, it'll click and switch to small pages, which are much more likely to be duplicated, and then transparent page sharing takes effect. This is funny because I think it was vSphere 5. When 5 first shipped, there was a bug in this. Not in this, but in how it displayed memory counters within vCenter. Everybody thought they were running out of memory on their host, and they were under heavy contention, and they were going to swap. And it turned out to be a UI bug because it's the way that it switched to page sharing. It wasn't actively being shown. Just know when you hit a point, it will flip and it'll start using small memory pages and will do transparent page sharing. You can change swap locations, use SSD cache if possible. Do not put on a thin provision data store or LUN. And you may want to put swap on local data store. So when you set up a VM, you get to select where the swap file is. Normally, it's a default setting is to put it in the same place as the VM, which for most cases is fine. But you may want to use SSD. I don't suggest putting it on a thin provision data store or LUN just because it's a little bit slower. And you may want to put it on a local data store. Now, if you do a vMotion of a VM from one host to another and swap is on local data store, it has to copy the swap file. But vMotion will do that. It handles that fine. The reason you want to put it on local, because you don't want swap traffic going back and forth across your storage fabric. And a lot of people will do things where they don't always replicate the swap partition because you don't want to replicate that to an off-site because it can be rebuilt later. That's up to you and how you want to do your DR strategy. But use SSD if possible, and then just may want to consider putting it on local disk. To allow abstraction of physical memory, there's a Virtual Memory Management Unit, MMU. It's either software or hardware. Software MMU virtualizes uses shadow page tables. Remember, software uses shadow page tables, so it's slower. Hardware uses functions built into the system. So we have Intel Extended Page Tables, EPT, or AMD Rapid Virtualization Indexing, RVI. Just know that those are ways to speed up memory abstraction. So a little bit about memory virtualization overhead. Software MMU virtualization has a higher CPU overhead. I mean, if you think about it, something has to manage those memory abstraction in the page tables, and that's the regular old CPU. So new processes of memory address space created, context switches, heavy memory allocation, all those involve the CPU. Hardware has fewer negatives. Go figure, right? Hardware's faster. Mainly just first time memory is allocated. Does it cause a performance impact? Afterwards, lookups are handled by the hardware, so it's not a big deal. Again, software slower, hardware faster. You can change the monitor mode of a VM. So we talked about monitor modes earlier, and now we kind of went through a few things. So the monitor mode of a VM defines how the hardware is abstracted. There are three available modes: binary translation of calls, software, and shadow page tables, software. So this is the old school method where the VMM ran on ring 0, and it handled all the binary translations, and all the shadow page tables for memory are handled by the CPU. Then we have HV, AMD or Intel VTX, hardware control for the virtualization for the CPU, but we're still using shadow page tables for the memory. So that's better, but not the best. And then we have HWMMU, hardware MMU, AMD or Intel VTX with EPT, and it's all done in hardware. So you're getting the hardware CPU virtualization and the hardware memory abstraction. Much better. Vsphare normally chooses the best option based on what your hardware support, but you can override it. So through several areas in vSphere, you can change what we call advanced attributes. You can change it on ESXi host, on virtual machine, or the cluster. And normally you only want to do these from VMware support. So don't just willy-nilly change these, and always make sure you document the original setting if there is one. And many of these settings can be found in the resource management guide. So we talk about some of these throughout the rest of the course. For the VM, the only one I normally ever change is the typomatic delay. And if you've ever RDP'd into a vCenter and then brought up a virtual machine console and started to type some text in, and you'll see it shoot off and keep repeating characters, it's due to the latency and the lag. It basically says, hey, I'm pressing the A key, and then the signal that says I've stopped pressing the A key gets delayed. So it thinks you've pressed the A key for like 3 seconds. It's really annoying. And so this is the only one I normally change. So that would be, it's in the resource management guide, or it should be. And that one is just keyboard.typomatic, TYPEMATIC, min delay, all one word, keyboard.typomatic min delay equals like, I think I normally set it like 2 million because it's in microseconds. So what that does is it allows you to set this and make it so that you're not repeating characters. And I'll show you this in the lab in a minute. A couple of things on BIOS settings. It's in the blueprint, so I'm going to say it. Kind of common sense, if you ask me. First one is often suggested to disable CPU power saving. You can do this if you want to. Modern systems and vSphere understand this stuff, but often people don't want it to kind of fluctuate the CPU performance depending on load. It's suggested to enable hyperthreading, and this allows cores to process multiple threads at once if possible. And also enable any hardware virtualization. Better performance required for some features such as EVC, enhanced vMotion compatibility, and fault tolerance. So no reason not to use those. We just went through a couple of slides showing you why software is slower and hardware is faster, so make sure you enable that. Disable NUMA interleaving in most cases unless a vendor or vSphere tells you not to. Enable wake on LAN support for NICs if you're using dynamic power management, because that's what it uses to wake up and shut down vSphere hosts. And just make sure you have the correct drivers for your hardware. Again, this is spelled out in the blueprint, but I can see it as common sense. Can be more confusing than you think, but always check the VMware hardware compatibility list for the correct versions. Check your version against the VMware HCL. Common to do that, and you also may need to download drivers from a vendor. Just make sure you get the right one for the right build of ESXi. Network configurations, fairly simple, tuning that. Use server class NICs, checksum offload, TCP segmentation offload, large receive offload, and jumbo frames if you need them. So cheaper NICs support less things and require the CPU to be involved more often. So get better NICs and you'll get better performance. Suggest use PCIe cards and select the appropriate teaming type, which we hit in depth in the physical connectivity lesson. ESXi storage, we talk about this in the storage lessons, but to kind of wrap it up here, confirm VA, support on your array, upgrade software if needed, choose the appropriate multipathing configuration, spread I/O over multiple paths if you can with like iSCSI, Sometimes you can't with like NFS. Configure the proper maximum queue depth. We talk a bit about that. For IP-based storage, do not route traffic, so don't put it on the other side of a router. It is supported now with like NFS, but I wouldn't do it. Use MPIO or multipathing with iSCSI or Fiber Channel. And enable write-back cache if possible, but confirm battery backup on the storage system if you do that. So that's it for the slides. I'm just going to run through a few random things here in the lab that I want to go over, so let's do that. So first thing, let's look at a VM. So let's edit the VM and take a look at what some of the settings are. So let's see, options. First thing I want to show you is MMU. We can set up basically the monitor mode. And here's the settings that we saw earlier. So by default, it's automatic. You can say software for instruction set and software for MMU, basically memory monitor unit. And then we have hardware for instruction set and software for MMU. And then finally, we have hardware for both. Normally, I'm going to leave this set for automatic. vSphere does a darn good job of figuring out what it needs to do. But occasionally, I will see things that say set another option for specific applications that need a different setting for the best performance. Swap file location we talked about. You can store it with the virtual machine or store it in the host swap file data store. You can select at a host basis where you want your swap configured per VM. We can also do some other things I'll show you here in a second. Just make sure there's nothing else in here I need. Let's see, advanced CPU. If you want to do any special hyper-threading configuration, such as an affinity, you can do CPU affinity here and specify that this stays on certain, basically, logical processors. I don't recommend you do that, but you can specify the numbers here using ranges. And again, I wouldn't recommend you do that unless you know really why you're doing it. Let's see, anything else? Oh, yeah. But I need to do it on a VM that's powered down. So go back to options. General, and here this configuration parameters is grayed out when the VM's booted up. So you can come in here, and these are some of the advanced attributes that I talked about. So let's see. Yeah, so the type-o-matic one is not in here. So what you can do is you can do an add row, and then it's keyboard.typematic min delay, and then I set this to like 2 million. So even if you hold a key down, it's got to be down for many seconds before it starts to repeat. But if you're having issues with repeating commands in a console window, that's how you fix it. And that's about the only thing that I change in there. So that's why I use that as an example. If you want to see what monitor mode is actually being used, the way you do that is you go to the directory. So I SSH into a host, VMFS volumes, data store 01. And then you go into the directory of a running VM. So let's just do our UI VM. That's not it. UI VM1. And we look at the VMware.log file. And just do a search for monitor. So in VI to do a search, you just do a slash, and then whatever you want to search for. It is case sensitive. Remember that. And it'll say, okay, here's your monitor mode settings in the log. You can tail the log if you want to while you boot to VM, whatever you want to do. But it says here's the allowed modes based on your hardware. So BT32 is the binary translation. So BT is binary translation. So this is software. Software. This is hardware for instruction set and software for MMU. This is HV. We saw that in the list that I had on the slide. And then this is HWMMU. This is hardware. So that's the one you really want. So these are the ones that are allowed. These are the ones requested. Basically, you set for automatic, and it's going to show all three of these. These are the ones that the guest OS prefers, which is a big reason to set the correct guest OS type when you set up a new VM. And here's the list basically saying which ones do you want against which ones are preferred. They are all. These are going to be in a preferred order. So it's going to prefer hardware, then it prefers hardware-software, then it prefers just software. And down here, it'll say settings are virtual execution mode is hardware, which is your instruction set, and virtual memory, virtual MMU is also hardware. So it chose HWMMU. So that you can't see that from the UI. You have to do that from a log file. But just thought I'd show you that. And the other thing I want to show you is how to set up host caching. So let's say you have local SSDs in your servers and you want to use those for local swap. So on Optimus, what I have done here is go to storage. I have a cache data store. Notice the drive type is SSD. I'm going to let you in on a secret. That's not really a solid state disk. I actually had some in these two, a couple of Kingston, small Kingston SSDs, and they have both died. They were cheap consumer grade SSDs I got for a steal on a Black Friday sale to play with, and they have both failed on me. So I wanted to show you this, so I lied. If you remember from our storage lesson, we talked about claim rules, and I created a claim rule and basically said, go claim this device, NAA dot some big long string of numbers for the device, and I set the option for SSD. So we talked about how to do that, and that's what I did, rescanned it, and now it sees it as an SSD. So I added it, formatted a data store, VMFS5. Then on each host that you want to do this with local SSDs, you go to configuration, you go down to host cache configuration. If you don't see it, do a refresh. If you haven't formatted the drive yet, you can do add storage, and it just starts the add storage wizard. Then we select, we do properties, and you say allocate space for host cache, and then you set a size. So you set whatever size you want, say OK. So you don't have to use the entire volume, but you can if you want to. So let's go back, VMFS volumes, and we want to go to the cache data store, and you'll see different stuff. So let's go here. You'll have a host cache directory, and it creates a bunch of these little vSwap files. So if we look, each of those is, what is that, comma, so a gig in size. So it creates a bunch of 1 gig little vSwap files automatically up to the space that you allocate for the amount of space you want to use. And then it'll go ahead and start using that. So if it starts swapping VMs to disk, it'll swap them to the SSDs, which makes it slightly less painful, and it's a bit easier on your storage fabric. So back to the slides. And that's the end of the lesson. So if I had to know what I wanted to study for the exam out of this lesson, I'm going to say know how to set a monitor mode, know how to confirm a monitor mode by looking at the VMware.log. Remember, that is in the VMs directory. It's not in var log on the vSphere host. You got to go out to the data store and look at the log file in the VMs directory. And then do a search for monitor in capital letters. I know how to do that. I know how to enable an SSD for caching mode. Hopefully you won't have to do a funky claim rule like I had to do, but if you did, you know, it's there and it's possible. I'd know how to do that. I'd know how to set attributes on the VMs. We'll talk about them for HA and the cluster and all the other stuff as we get to it. But for a VM, I'd know how to set that attribute where I showed you how to do the typematic minimum delay, and I'd know how to do that. And let's see, I think that's about it. I would have a good idea of how to look at, oh, I know what I want to tell you before I get there. Real quick, one other thing I want to show you. We talked about NUMA access. We talked about don't give a VM more memory than is assigned to a NUMA node, basically a CPU in your system. And one thing that I do want to show you is as you assign CPUs, we now have the option of virtual sockets and cores per socket. This was actually has been a feature for a while, but it was exposed in the UI in 5.0 and 5.1. You want to try to match those. So by default, I only have 2 vCPUs here. But let's say I had a VM. Let's pick that VM. And I was going to set this to a larger number. Let's say I wanted to have 8 vCPUs. But I only have 6 core CPUs in my server. So I have two CPUs, 6 cores each, total 12 cores. We say, why don't you just set this to 8? Well, because I want it to understand the underlying architecture. So what you should do there is set it to 2 and 4. So 2 by 4. So 2 sockets with 4 cores each. Try to closely mimic the underlying physical server hardware as best you can so that the guest OS tries to mimic that and it tries to schedule things on the appropriate CPUs. And basically what you're trying to pass through is NUMA. You want it to understand the underlying NUMA architecture so the guest OS uses it, therefore the CPU scheduler can use it. So I'm not saying you have to set it to 2 by 6, but if you're going to go above more cores than it's in a single socket, I would definitely try to mimic that and split those equally as best you can. The reason that came to me is I was going to say I'd understand NUMA and how to assign. So if they say, hey, deploy this VM understanding that the physical configuration of the server is 2 sockets with a total of 128 gigs, 64 gig per socket for NUMA, understand how you might want to deploy that VM. That's kind of a stretch on what I think you'd see on the exam, but understand that just in case. But I think that's it for this lesson, and I look forward to seeing you on the next one.